So again, I'm going to echo what Jeff said. I wasn't sure what the audience would be, and we had a lot of ground to cover because some people know what this is about and some people have no clue. And it's certainly, in some ways, very in place and very out of place with the previous two speakers. So I'm just going to have to do my best. We cover a lot of ground in metamaterials. It really covers everything from electromagnetics to optics. I'm not going to talk about optics today, but we have a large optics program. And it also encompasses other branches of physics, including acoustics, thermal flow, and many other things where metamaterials has now creeped in. So I'm just going to give you a little bit of history, and I have way too many slides, so I'm just going to keep going and hopefully show you some interesting things. Oh, that's nice. So we have a center on metamaterials, and these are some of the faculty here. Right now we have about 56 members. It's probably the largest effort in metamaterials, I would say, in the world, certainly in the US. We've been able to attract a lot of new people here, including Mike Nicholson and Willie Padilla. Again, I can't cover everything everyone's doing. Steve Cummer works in acoustics and many other things, and Mike works in optics. And Dan, our host, has been working with me since basically I got to do. So we view materials. This is a very physics-oriented way of viewing materials. Materials are you can tell a material by its properties. For optical properties, we're interested in two parameters, a few more, but two basic ones: electric permittivity and magnetic permeability. Electric permittivity measures the response of the material to electric fields, and magnetic permeability measures the response of the material to magnetic fields. And that's important if you want to manage electromagnetic waves, which consist of oscillating electric and magnetic fields. So if you want to really grab a wave with both hands, you have to control the electric and the magnetic properties. And materials have a certain number of properties that they have that enable us to make interesting devices. But they don't span the entire spectrum of what should be available. So this is the most physicsy slide I'm going to show. If you look at a material under a microscope, you know that it's composed of atoms and molecules. If you apply an electric field, you create a charge displacement, and that creates a dipole moment, an electric dipole moment. And if you apply a magnetic field, you change the spins if it's an inherently magnetic material. If not, you can create little currents running around, and that's the essence of magnetism. So there's two types of response, electric and magnetic, and they both lead to these dipolar responses, induced electric or magnetic dipoles. And now if you look at a material the way a physicist might look at a material, you see that it's just really composed of a bunch of polarizable dipoles. And the strength of this response and the interactions really define a material for us electromagnetically or optically. So all of that microscopic detail gets folded into these macroscopic parameters, which we use for engineering and other more, I'd say, convenient ways of designing devices and applications using materials, at least for optical applications. So that's the basics of what a material is. And now I can tell you what a metamaterial is. I showed you that an actual material just is composed of all these dipoles. Well, you don't have to rely on atoms and molecules anymore. We can actually create little objects that are macroscopic but behave in the same way. They are polarizable dipoles. So this picture here indicates that we can create a structure with a bunch of these little structured elements, and electromagnetically, if the wavelength is much longer than the structure, it looks like a material like any other material, except it has really, really interesting properties that you can't get in nature. So for us, we're creating artificial materials, and these are examples of things that we've used, in which we replace the atoms and molecules with dipoles conceptually. And that turns out to be a hugely useful design tool. It's not a thing, even though these are things, it's really a design approach that has allowed new design and engineering techniques to emerge, and that's turned out to be a lot more valuable than I first thought when we started doing this. And one of the reasons that this field has grown so quickly and has attracted so much interest is because there's so much flexibility in it. And it leverages a lot of mature fabrication techniques that weren't around when the first effective medium ideas were considered, as also it leverages high-speed computing and the advances in computing that have happened in order to make this a reality. So this type of metamaterial now has really caught fire. And here's just a cast of characters of some simple examples of things that you'll see in my talk, ways of creating artificial dielectrics, an artificial permittivity. Here's how you can create an artificial magnetic material, just a loop, in which if you apply a oscillating magnetic field along the axis, you create a current, and that's the essence of magnetism, as what I showed. Or you can create a resonant electric response. And if you do that, you can really get any kind of material response. And again, I'm showing the origins of metamaterials. It's grown beyond this, but this was one of the first things that was noted. You can get basically an artificial dielectric, where your dielectric is greater than 0 and just kind of constant. But you can also get these resonant responses, and these resonant responses are interesting because either mu or epsilon, you can have regions where mu is greater than 0, significantly greater, or negative, or between 0 and 1, and the same with epsilon. And that's interesting because some of these properties, until recently, were not really looked at or accessed for applications, and even the resonances weren't really leveraged, especially lower frequencies, as you might think of doing if you were to think of these structures as materials that whose resonances can be tuned anywhere in the spectrum. So this is what you can do, and in 2000, well, actually before that, in 2000, all this technique was harnessed to realize something that had been predicted many, many years ago by Russian physicist Victor Veselago, who said, you know what, there's no materials that have simultaneously negative values of epsilon and mu. They just don't exist. And he said, in addition to wondering why they don't exist, he said, what if they did exist, what would their properties be? And surprisingly, he found that they change a lot of physics. And so this is just a list of things that he found. And this, basically, you can boil down to such a material with negative epsilon and mu as a material that has a negative index of refraction. I won't go into the reason for that, but n is equal to the square root of epsilon times mu. If epsilon and mu are both negative, this is a positive, so you have to choose the square root, and you have to choose it negative if epsilon and mu are both less than 0. So it was a very unusual material. And here's a bunch of pictures that were from Victor Veselago's article showing different things you could do with this negative index material. I just want to show this diagram. I think he was the first to do it, where he showed all materials being parameterized on an epsilon and mu space. And he pointed out that in this third quadrant here, there were no materials. You can find materials here, here, and of course here, but not here. And this has become known as the Veselago diagram, which is one way of parameterizing materials. So the real result of a negative index material is that if you have an interface where you have refraction, if the index is negative, the refraction goes to the other side, so it bends light to the wrong direction if this is a negative index material. And that's interesting because there just are no materials that do that in nature, and he conjectured why that might be. But in 2000, we introduced this material here, and you see these rings, and I call it material. I'm used to calling it material. You might think it looks like some weird electrical engineering construction. But again, at the wavelengths where this was used, these are wires giving a negative electric response, and these are rings giving a negative magnetic response, negative mu, negative epsilon. And so we reported this in 2000. This really touched off the field of metamaterials. We did an experiment in 2001 showing, confirming Veselago's conjecture that a wave coming in would bend to the wrong side of the surface normal, and that was done here. And so the concept of negative refraction was demonstrated using these new and interesting materials. And again, we just assembled things. They weren't new in the fact that this is just copper on circuit board and copper posts or brass posts. But combining them in a certain way gave us insights that we just didn't have before. It created a lot of controversy. It was not without controversy. A lot of people doubted metamaterials. They doubted negative index. Just a lot of doubters. You can see by some of these titles is wave refraction, negative index media, always positive. Problem of left-hand materials, as they were called at the time. Lots of negative papers, and also carried in the popular press. You can see heat and light. Does negative refraction really exist? And then here is everything as it seems. So there was a lot of controversy about metamaterials at the time. And in the end, I won't go through the entire history, but in the end, it was all decided positively that yes, they exist. So that showed the possibility of using artificial structures to make something that couldn't exist, that didn't exist in nature. But there's obviously a lot more flexibility you have because you can create essentially anything you want on demand. So, for example, gradient materials are very, very interesting. They're an interesting way to control light or electromagnetic waves. And it's very easy to do just by controlling geometry. For example, here we can increase the gap size. And if we increase the gap size, it turns out to create a decreasing permeability. So we're changing the magnetic response at every single point. So we can create a spatial gradient. Likewise, all we have to do is increase the height of these little I-beams, and we can actually create a gradient in the permittivity. So this turns out to be a great match for gradient index optics. You can have huge variations in index or in the parameters. You can control the anisotropy. You can create independent gradients in electric and magnetic response. So in the end, you have what amounts to an unprecedented amount of design flexibility. It's unprecedented because natural materials you just aren't able to control like that, especially to have both electric and magnetic response. So here's just a brief example of one thing we did, a very simple gradient index lens. So this was just done to focus light. This was at 10 gigahertz. This is at microwave frequency, so you can see the structure and you see this circuit board construction that we used. Won't go into the details of the experiment, but you can see it was a very large index change, nearly 2 from 1. If you think in terms of optics, index change of maybe 0.1 or 0.05, or maybe even less, would be considered huge. And here we're getting these gigantic swings really just by this patterning approach. So just for something practical, we had a nice project with Toyota in which we looked at a collision avoidance system and looked at the lens on that system and asked, could we reproduce the focusing properties of that lens but reduce the profile using a metamaterial. And this was work that was done, in fact, with Nan Jokers. This was the stack-up of what was built to work at 77 gigahertz. And you can see the profile of the lens that was created versus the duplicate of the lens that was in the system, and you can see the reduction in profile. Again, it had the same performance or better performance than this lens. Really better in most metrics except cost. This is probably a 15-cent lens in production quantity, and this is not. So another thing you can do is really use metamaterials to create an aperture and do something like a hologram. And this, again, was just to show the flexibility. Again, work done in conjunction with Nan Joker's group. And you can see if you just apply the principles of photography, if you want an object that looks like this in the far field, you have to put its Fourier transform. And if you want to make a phase hologram, this is the phase distribution. They're a little bit hard to see, but again, we can create this phase distribution just by changing the effective index using these I-beam type structures. And we have a little interpolation chart whereby we can change the refractive index. And again, this is now for 10.6 microns, and we're getting a refractive index change that goes from 2 to 5, which is a huge gradient. And you can see what this structure would look like. And actually, here's the fabricated structure. And if we look at the experiment that was done, here's the sample, closer and closer, and you can see these little cells with these elements, which give us basically pixels of different phase advance, and an experiment done at 10.6 microns, and the D, the U, the K, and the E kind of slid off in the far field. So this was an example just with a few layers of lithographically produced structure, again, gradient structure, really exercising what metamaterials can do. You can do things that occur in conventional optics, but you may be able to do them better. So one quick statement about this experiment, which really we've been seeing a lot of interest from the media and from various sectors in the negative index and the scientific community, but this experiment in which we created a gradient structure that acted as an invisibility cloak really drew a lot of interest. This was the experiment that was done. This is a radial structure, and we had to control the permeability from 0 to 0.25 in order to make this structure and also control the electric response. So that was a huge challenge. You really couldn't do this with normal materials very easily, if at all. And in the end, if you do it, this is the type of structure that you could get. This was a simulation, and this is the measurement. So this was done again at microwave frequencies just to show the concept. But you can see that these two field patterns simulated for this weird material and the actual metamaterial measurement are nearly identical. For all intents and purposes, you'd have to look closely to actually see that there is structure there caused by these rings and that it's not a continuous material. But otherwise, it looks pretty good. And since then, this was done in 2006. Since then, numerous experiments have been done, and the cloaks have gotten better and better. There was a lot of interest in that. This is just some of what happened in 2006. This is, I just like this picture. I always show it. This is my former postdoc, Dave Schurig, who was wearing sunglasses on his third interview with Fox News. It really grabbed the front page news, whether deservedly or probably undeservedly. And it still shows up various time to times. I wanted to show this because the two things I've just shown, including Veselago's diagram, showed up on the Big Bang Theory. And you can see here it says metamaterials in this region where epsilon and mu are both less than 0, which is really interesting. And also our cloak appeared on an episode hanging out there. So the concept of metamaterials definitely struck the science nerve. And most recently this year, we got this question on Jeopardy, or this answer, and the category was how innovative, and the question was, what is invisibility? So this was stays sort of relevant even now. So now I want to switch to something real in the time that I have. I've talked about one particular type of metamaterial, which is this volumetric idea that we're putting dipoles in and creating an artificial material that goes through some volume, and that's really interesting. Maybe less useful for applications right now just because of the form factor. But we can also create these guided wave metamaterials. And again, we can use these complementary metamaterials where we pattern structures or patterns into one plate of, for example, a waveguide. And if we do that, we can replace those again with dipoles. But the difference is in a structure like that, because there's openings, these will also radiate. So they form the basis of an antenna. And here's an example of a radiation pattern. We're feeding it with a waveguide. And again, by tuning the geometry, you can tune where that resonance occurs, and so you've got the basis of an antenna. This now allows us to really reimagine the aperture. I'll come back to what this is, hopefully in a few seconds. But we can take now something, this design flexibility that metamaterials give us, and really recreate apertures both for imaging and beamforming. Some of you may or may not know much about phased arrays, but if you want to direct a beam somewhere, there's really been historically just a couple common ways of doing that. One is by fixed dishes, which are heavy, and if you want to make them reconfigurable, you have to put in gears and move them around. Or you have these things called phased arrays. Phased arrays have a bunch of antenna elements, and in order to steer the beam electronically, you have phase shifters behind each antenna with a feed network if you have a passive phased array. And you gang this thing together, and you have something maybe that looks like that. Very popular in the DoD because the DoD is pretty much the only entity that has the money for one of these things. They're very expensive, they have a large power draw, and so they are not ubiquitous solutions. Likewise, even worse is the AESA, which is an active electronically steered antenna. And again, this is even worse because each antenna is backed by a phase shifter and an amplifier. So you have a TX-RX module behind every single antenna. So this is an architecture where we can think of using metamaterials and their properties to address a system that currently, or at least an application that currently had very few solutions other than these large cost ones. So here's a metamaterial version of creating a reconfigurable beamforming or, in fact, imaging aperture. And here I've just put in something where we're going to imagine that we can tune the resonances of these materials, feeding them with a wave, just one amplifier. And again, the change of these materials can be done with very low voltage or very low power, so that this can be a very different type of structure. It's hard to go into this in detail, but I'll just show you that picture. And here's a conceptual picture of what such a aperture might look like. So this is just a waveguide where I've etched in a bunch of these complementary metamaterial elements. If I can tune them, then I can create a reconfigurable aperture. And again, just by geometry, we can go from on and off or possibly other types of things. Again, not enough time to go into that. So there's a lot of ways of tuning, and this creates the science part of this concept. One is by photo excitation. So this is an experiment that was done by Willie Padilla in 2006, where you just have a semiconductor substrate, you blast it with a laser, and depending on the strength of the laser, you can turn selectively the resonance of these rings on or off, and so you can change the transmission. So this was something where you just hit the whole array. We like that concept. We like to hear. This was work that we did again with Dan Jokers, trying to create a integrated solution where you might imagine really tuning each element cell by cell and creating really a reconfigurable metamaterial. It can be done. Here's an example, and again, a conceptual example of creating a Schottky barrier you might do. And as you change the voltage, you change the depletion region, so you change the conductivity near the element, and you can turn on and off a beam, for example, just by voltage. And again, an experiment that was pioneered in 2006, again by Willie Padilla, that was done at Los Alamos. And you can see as a function of voltage, they were able to turn on and off the transmission and the resonance. So there is a path there, but there's a lot of ways to tune. So I wanted to show this chart. We're interested in all sorts of tuning methods, but if you want to start thinking about turning this into something commercial, something stands out. And this actually, I can't take credit for this chart. This comes from Nathan Kuntz at Kymeta, who did a little marketing study and looked at all these different tuning mechanisms. And something that came up at the top was liquid crystal. And liquid crystal is interesting because there's a huge industry behind liquid crystals. That's the display technologies. And something like this, the raw cost of creating this, we'll call it, it's a display, but we'll call it a tunable aperture, is really in the hundreds of dollars. And there's thousands, tens of thousands, maybe hundreds of thousands of individually addressable elements. So the industry already knows how to do this. And this was the vision of Nathan Kuntz, who's shown here. He was a student and postdoc in my group at Duke, and then went on to become now the CEO of Kymeta, which is using this concept to create tunable antennas for satellite communications. So this was picked up at Intellectual Ventures and then attracted the attention of Bill Gates, and now has become really, they completed round C, and they're now starting to ship products in this space. So there's lots of obvious applications of this, much more than we realized when we started this entire endeavor. Again, this is just a picture of the antennas. And this shows the beam forming in the frequencies that they're using for satellite communications. So I've done a really quick sprint from the basic science to just a couple of examples of what we're doing, and I just will have to close here because there's so much to talk about. But as part of this little exercise, there was a lot of other marketing done, and a few other sectors that were recognized: radar, imaging, comms. And since that time, Chimeta was started, I think, in 2011 or 2012. Since that time, two more companies were spun off, and the third one's in the works. And this is just one portion of what we talk about. We are doing a lot more. These are all in the RF domain, in fact, low RF domain, and there's a lot more to explore in the realm of metamaterials, including in all the other branches of physics. So I hope I haven't overwhelmed you too much. There's far too much to talk about. So I'll stop here and just ask if there's any questions. Thank you.
All right, questions for David? You stunned them.
What is the actual composition of the patterns that you're making? I didn't quite catch what that.
What do you mean?
Like the eye shapes and the hoop.
What are they made of, perhaps?
Yeah.
Oh, those are just metals. So copper, this is leveraging just circuit board technology. So it's copper patterned on a dielectric substrate.
Yeah, it's pretty simple, interestingly enough. Yeah, using printed circuit board technology to demonstrate a lot of this.
Or other types of lithography.
So you said the Tokyo lens was cheap. Was that expensive? How expensive compared to the 56?
Oh gosh, it was using an experimental LCP board from Rogers, and the pressing and then everything. I don't know. It was ungodly expensive.
It could be inexpensive. Yeah, I think it could have. The cost could have been brought down because it was the material was experimental, but I think the ultimate cost of that material wouldn't have been too high, and it was a straight lamination 3D process.
You wouldn't beat just a
You can't beat
simple
plastic,
dielectric
yeah, right.
plastic lens.
I mean, that's tough.
And really, that was done before. It shows the importance of getting together with people in industry and doing the right sort of marketing. We were working with an experimental research group at Toyota, not the group that would actually say, okay, would this be a product? And looking at the first sector we looked at was the satellite with intellectual ventures, and seeing the high-end systems and the expensive systems that were out there, and actually blocking ubiquitous adoption of satellite communication for internet or other types of comms. Really was eye-opening. So it's really important to kind of work that strategy, because for metamaterials there were a lot of opportunities. No one realized that until around 2010. And it started in 2000.
And most components in a car cost pennies. Yeah. So you can't add something to a car that's extremely expensive. Yeah. Other questions? Jeff, you had a question?
Yeah. So it seems like some of the technologies are fairly simple from a perspective of making them. Is that true? And if that is true, what are the major challenges for these spin-outs?
The major challenges now for the spin-outs is really market risk. All of them have a product, and I think the simplicity is key. It's important that it be simple, just because we go here thinking about, can we do something interesting scientifically, to a company which says we have to have suppliers, we have to have supply chains, we have to have manufacturability, we have to have all these things, and simplicity is really a driver, not complexity. Complexity only helps as barrier to entry, but you just want to be able to produce something reliably. So for that reason, the fact that metamaterials can leverage commercial mature technologies in order to create these products, you're just combining things and really being assembler of what's out there is truly advantageous in this case.
So is there a major difference in the market acceptance from current technology to this? So, like, they have to redesign systems around this technology, or?
There was initially, metamaterials had the rap. I've given you the bad and the good. So the science was interesting, but it created a bad rap in industry because it looked like a hobbyist thing that had no application. So the biggest barrier was, oh, we know that invisibility cloak thing. That's cute, but that's not for us. Also, the entrenchment of phased arrays as a solution in dishes was pretty strong. But once this thing sort of took off at a high level, and a few key players got on board, a few key satellite companies like Inmarsat and Intelsat and some of these other really big O3B, some of these other ones, the acceptance has really flipped over.
You know, we see this with technologies. I went through through the transition of the lasers. Oh, interesting, but physicsy. Yeah, what's that good for? Right? Yeah. You know, to the ubiquitous use of lasers today. And so I think metamaterials is on the same trajectory. So let's thank David Smith.